This is our presentation about the AES and RSA cryptography. I am José Ambrósio.
I'm Gilberto Guerra.
Our project aimed to create an educational software tool focused on teaching individuals the purpose and functionality of AES and RSA cryptography. Going beyond theoretical explanations, the objective was to provide a user-friendly interface with interactive elements, simulations, and practical examples to enhance hands-on learning. We sought to demystify complex cryptographic concepts and address challenges in understanding by catering to users with varying technical expertise. The software intended to be a valuable resource for academics, institutions, and professionals, offering curated educational materials and encouraging continuous exploration of the field. Overall, the goal was to contribute to a more secure and knowledgeable digital community by promoting a comprehensive understanding of AES and RSA cryptography.
Encryption is the process by which information is converted from plain text to a form that cannot be used by an unauthorized entity. Decryption is a process of converting this unreadable information back into the original form, usually so that the intended recipient of this information can read it. Encryption and decryption are almost always used in internet connections, websites, as well as calls, video conferences, and so on.
How does encryption work? For encryption to work, there are essential elements such as the plain text, an encryption algorithm, a key, and the ciphertext. The plain text is the starting point of the encryption process. Plain text is the original human readable data that you want to protect. It could be a simple message, a file, or any form of information that you want to keep confidential. Then there's a need to have an encryption algorithm, which is a set of mathematical procedures or rules that dictate how the transformation from plain text to ciphertext occurs. It's the core mechanism responsible for converting the readable data into a secure and readable format. There are examples of encryption algorithms such as the AES, which is a symmetric encryption algorithm widely used for its efficiency and security nowadays. There are other examples such as the RSA, an asymmetric encryption algorithm. Then there is the DS, which is another symmetric encryption algorithm, though is nowadays considered outdated and less secure than, for example, the AES and the RSA. Then a key is essential because it's a crucial piece of information that is used by the encryption algorithm to perform the encryption process. The choice of the key is a critical factor in ensuring the security of the encrypted data. The key can be, for example, symmetric encryption key, which is used for both the encryption and decryption processes. This means that both the sender and the receiver need to have the same secret key. However, there's the possibility to have an asymmetric encryption key as well. In this type of encryption, there is a public key and a private key. The public key is used for encryption, while the private key is used for decryption. This enables secure communication without the need for both parties to share a common secret key. And then we have the ciphertext, which is the result of the encryption process. It appears as seemingly random and a readable sequence of characters. The purpose of ciphertext is to be challenging for unauthorized parties to understand, even if intercepted. The ciphertext is what gets transmitted over insecure channels, since it does not reveal the original content without the appropriate key for decryption.
The process of decryption starts with the ciphertext that is generated via encryption. The goal is to return this to its original usable form. The algorithm used is the same, should be the same one that is used in encryption. There are symmetric algorithms such as DES and AES, as well as asymmetric algorithms such as RSA. For symmetric algorithms, the key remains the same as in encryption, and usually there is some difference in how the algorithm is executed. Meanwhile, for asymmetric algorithms, there are separate keys. One that is used for encryption and another one for decryption. After decryption, the plain texts should be once again available. It should be identical to the plain text that was first encrypted.
There are different types of encryption algorithms. There are the symmetric algorithms and the asymmetric algorithms. Symmetric encryption involves utilizing the same key for both the encryption and decryption processes. This shared key is applied to both secure and unveiled information. The speed is an advantage for symmetric encryption algorithms since they are quicker than asymmetric encryption algorithms. They are known for its speed for completing both the encryption and decryption procedures more rapidly than the symmetric encryption algorithms. There are examples of symmetric encryption algorithms, such as the AES and the DES. Both of them use the same key for both encryption and decryption processes. Symmetric encryption provides a streamlined approach to secure data by employing a single key for both encoding and decoding. The efficiency of this method makes it suitable for scenarios where speed is a critical factor. While effective, the challenge lies in securely sharing the common key between communicating parties. It's essential to have a secure way of sharing the key that will be used for both the encryption and decryption process. Because if, for example, or a person that is not supposed to read the message is able to get this key, this person will be able to read the message. So how this key will be shared is an essential part of guaranteeing the security of symmetric encryption algorithms.
Asymmetric algorithms, they use different public and private keys for encryption and decryption respectively. One main problem with asymmetric algorithms is that they are usually slower than comparable symmetric algorithms. So for encrypting large messages, files, text, videos, it is usually better to use a symmetric algorithm. But the advantage of asymmetric algorithms is that you don't need a secure channel to exchange keys. You can make, for example, for RSA, you can make a public key that is available to anyone, and only you have the private key to read encrypted messages. Not only can you exchange a key for a symmetric algorithm this way, you can also provide other security functions such as digital signatures. Examples of asymmetric algorithms include RSA, Kalman key exchange, and there are schemes based on elliptic curve cryptography.
Now I will talk about one of the encryption algorithms we've implemented on our project, which is the AES, Advanced Encryption Standard. The encryption process consists on transforming blocks of data, typically 16 bytes or 128 bits, for enhanced security and confidentiality. This process means that all of the bytes of the message will not be encrypted at the same time. Instead, the message will be divided, then encrypted one block after another block until the end of the message. So until the message is completed encrypted. There are essential elements for the AES encryptions. And one of them is the plain text, which is the starting point of the encryption process, as is the original readable data that undergoes this transformation. The next step is the key expansion, which involves deriving a set of round keys from the original secret key, extending the security of the encryption process. After having our plain text, we have to have a secret key that can be generated randomly, and this key, for example, would be used for both the encryption process and the decryption process. This key can be as well generated by, for example, a password, and that the user that wants to encrypt the message have to insert, and the secret key will then be generated using this password. And the same has to be applied for the decryption process, in which the user that wants to decrypt the message has to write the same password, and then the same key will be generated for then decrypt the message. After the key expansion process, there's the initial round, which involves shoring the plain text with the first round key, initiating then the encryption process. Then there are many rounds of encrypting this message, depending on the key size, which can be 128 or 192 or 256. And there is a different number of rounds. For the 128 key size, there are 10 rounds. For the 192 key size, there are 12 rounds. And for the 256, there are 14 rounds. Each round of the encryption and the decryption process consists of substitution using byte substitution, and there is the permutation using shift rows, and there is the mixing using mixed columns, and then the round key addition. Besides the final round, every other round use the mixed column. So in the final round, the mixed column step is not used. And then there is the cipher test, which is the last step of the encryption process, which is the final output of the encryption process, where a secure and transformed version of the original data is generated. The byte substitution, in this step, each byte in the state matrix is replaced with a corresponding byte from the S box, which is a predefined substitution table. The purpose of this step is to add nonlinearity to the encryption process. Then there is the shift row step, which is a row-wise permutation. In this step, bytes in each row of the state matrix are shifted to the left by an offset during the encryption process. The first row remains unchanged. The second row shifts by 1 position. The third row shifts by 2 positions. And the fourth row shifts by 3 positions. The purpose of this step is to provide diffusion and spread the information across the rows. The other step is the mixed columns. In this step, each column of the state matrix is multiplied by a fixed matrix, followed by addition, using the Galois field multiplication table. This mechanism ensures that the output bits depend on multiple input bits. The purpose of this step is to increase diffusion and ensure that changes in one byte affect the entire block. Then there is the round key addition step. In this step, the state matrix is stored with a round key derived from the original encryption key. Each byte in the state matrix corresponds to a byte in the round key. The purpose of this step is to introduce the secret key into the encryption process, ensuring that each round is dependent on this key.
AES decryption starts, so it starts with the ciphertext, and based on the same key, it performs the key expansion as usual to get the round keys and the subsets of the original secret key. Each round, the operations performed are the mixed column, shift rows. All of these are inverted for each round. So the final round, it doesn't include the inverse mixed column step. After the decryption, each 16-byte block of ciphertext should be converted to the original section of plaintext.
After explaining the AES encryption algorithm, I will now show our software. This is the initial window of our AES and RSA cryptography software. We have options for the AES encryption and decryption, for the RSA keys generation, and for the RSA encryption and decryption process. When we click on the AES encryption button, this window opens, and this window allows the user to encrypt messages using the AES algorithm. We have a field for the user to input a password of his choice or of its choice, and there's also the field for the user to input the message which will be encrypted, and then there is the output field which will show the encrypted message. And there are 2 options. The user can write a password and a message to encrypt using the graphical interface. For example, in this field, the user can write a password, but the user can also select this button to select a password from a text file. The same happens for the input message. The user can, for example, write FHSU is very beautiful and encrypt this message, or the user can also select a text file to encrypt the message which is in this text file. I will show first the encryption process using user's input directly on the graphical interface, which is writing the password and the input on these text fields. After writing the password that will be used both for encryption and also for decryption, because AES is a symmetric encryption algorithm. Then I write my message, which will be encrypted. And then I can also show the encrypted message directly here on this output text field, or the user can also select a text file to store this encrypted message. But I'll use this option to show the encrypted message here on this output text field on my graphical interface. After I click on the encrypt button, the output text field shows my encrypted message, which is not human readable, which is the purpose of encryption. It appears like random characters that doesn't have any meaning. The user cannot guess that this encrypted message or this ciphertext, which is here in our output text field, was generated from this plain text. FHSU is very beautiful. So this means that our encryption process works well, as seemingly random characters were generated after our encryption process. On our right side of the graphical user interface, there are the steps that are involved in the encryption process. We have here our initial key, that is here. And then from this initial key, the round keys were generated. We can see here, for example, round key 1, and then round key 2. These keys are, these round keys are related to this block, which is the first block of our plain text that will be encrypted, as in the AES encryption. The message is encrypted by blocks. The message is not encrypted all at the same time, but instead the message is divided in blocks of 16 bytes. So this is our first block of 16 bytes. This block will be encrypted using this, in this case, 14 round keys. And then we have here the ciphertext that was generated from this first block. And then we have our second block that is this part, beautiful, and the dot. Then this block is then encrypted, which is our second block from this message. As this message doesn't have 16 bytes, we had to pad the message. So we add another bytes, or we add other bytes until we complete a block of 16 bytes now, and then we can start the encryption process. We pass through all of the 14 rounds. We have here our round Q1, and then we have our round Q2, and we pass through all of these rounds, 14 rounds in total, until we have our final ciphertext here. Here we have in numbers, and then this is our final ciphertext, and this is our final encrypted message. As you can see, our encrypted message, which is our ciphertext, is completely different from our plaintext. This means that our encryption process works well. I will now show the decryption process. I will use the same password as we are working with AES, which is a symmetric algorithm. So I'll be using the same password for decryption. This is our decryption window, which is similar from our encryption window for the AES. The difference is that instead of encryption, we will be decrypting. So we will have here our decryption button. Now I will try using an almost similar password, but not equal, to try to decrypt our encrypted message. And as you can see, we are not able to recover our original plain text. This is the output. I will now try another password, which is kind of similar, but instead of using lowercase characters, which is our original password, we are using uppercase characters. We will try another time to decrypt our encrypted message. As we can see, we're still not able to recover our original plain text. And now I will use the same password, which was used for encryption, to try to decrypt my encrypted message. And as we can see, if both the user that sent the message and the user that received the message have the same password, the user that received the message is able to recover the original plain text, which is FHSU, is very beautiful. So our encryption and decryption algorithm works. We were able to recover our plain text. And here on the right side, we have the steps. We have our initial key, and we pass through all of the rounds again. We have the initial round key, we have the round Q1 here, we have the round key tool, and we will pass through all of these rounds until we end our message. Similar to the encryption process, on the first block, which we have right here, this is our first block. We will go through all of these 14 rounds, but we will do the inverse of the encryption process. Then we will go to our second block of characters, of the second block of 16 characters, which we have here. Then we'll go through all of these 14 rounds again for this block until we end this process and we recover our original message, our plain text, which is the decrypted message, and it's showing right here. FHSU is very beautiful. Now we will try to encrypt another message, which is a bigger message. I will now encrypt a bigger message, and we will see the results. We will now use a different password and a bigger message. We can see here our encrypted message and the steps here, the round keys here on the right. And we are still able to decrypt our message. And I will now use our test file 3, which has an even bigger message. And we also see the results of the encryption and decryption process. We have here our encrypted message. Our ciphertext is bigger compared to the other message, as our plaintext is also bigger. And then we will decrypt this message. And we have here our plaintext recovered for this ciphertext. So our encryption and decryption process works for smaller messages and also for bigger messages with 2-3 sentences. Now we will show the AES encryption and decryption process using text files instead of using instead of using the user's input directly on our text fields on our graphical user interface.
So here I'll demonstrate AES encryption and decryption using files. So here I put in 2 password files and 1 message I'll use to encrypt. So here I can click read these options to read and write from files. So here I just select one of the password files and this message file. And then here I also created this AES encrypted to use as output. And so here the the round keys pop up as usual, and yeah, let's decrypt here. I'll try decrypting using a different password to here have the encrypted file. Write it to say as decrypted. Here the round keys appear as usual. If I click, if I go to do you know why it's so the round keys show up here as usual. I can go here. If I go here to open the decrypted file, you can see that it doesn't show it hasn't been decrypted correctly. And if I go back and if I go back and select the correct password, there I'll just click decrypt again. If we open this now, so here we can open the decrypted file and to decrypt, and here it should show the original message from this file. That's the AES encrypt and decrypt the files.
Now I'll talk about the RSA, which is another encryption algorithm that we implemented in our project. The RSA is an asymmetric encryption algorithm, which means that there is a public key which is used for encrypt the message, to encrypt the message, and there's a private key which is used to decrypt the message. RSA RSA is a widely used public key crypto system for secure communication and digital signatures. The security is based on the difficulty of factoring the product of two large prime numbers. The public key is used for encryption, and the private key is used for decryption and digital signatures. The security of the RSA relies on the difficulty of factoring the product of two large prime numbers. It is considered secure as long as factoring large numbers remains computationally infeasible. The key length is crucial for the security of the RSA. A longer key length provides higher security, but also increase the computational complexity. There are some steps used for the key generation. The first one is the selection of two large prime numbers, P and Q. Then we have the modulus computation, which is calculated as the product of the selected prime numbers, which is n equals P times Q. Then we have our Totient calculation, which is determined using the Euler-Torsion function, which is phi of n equals to the product of P minus 1 and Q minus 1. Then we have the public key selection, which is a public exponent, shows to which is a public exponent, but we need to ensure that it is coprime to the calculated totient. And then we have our private key calculation, which is the private exponent D, and is computed such that D times E is equivalent to 1 modulo phi of n. There are several applications for the RSA. The RSA is commonly used to secure the transmission of sensitive data over networks, such as in HTTPS for secure web browsing. In digital signatures, the RSA is used to create digital. In digital signatures, the RSA provides a way to verify the authenticity and integrity of digital messages. The RSA is also used in key exchange, which is used to allow secure establishment of shared secret keys between parties. The RSA is also a fundamental component of the public infrastructure, where it is used for creating digital certificates and ensuring secure communication in a networked environment.
The RSA algorithm, encryption and decryption are relatively simple. So the first step for encryption is to convert the plain text into a numerical form. This doesn't increase security itself, but since you need to perform exponentiation with the message, anything works to convert it to a number. To compute the ciphertext from this plain text, you just raise the plain text to the power of the private public key E modulo n, and then this just gets you the ciphertext. To decrypt this ciphertext, you just have to raise it again to the power of D, which is the private key, and again modulo n. You get the original numerical x back, and then you can convert this for a number back into plain text in the same way that you did when encrypting. I'll show you encryption with RSA using user input. So here, something that you didn't see in AES is these default keys. They're taken from where they're generated here. I could, for example, generate these new ones to put in here. So here I'll just put in so here's an example message. You can encrypt this here. And then to decrypt, you just here put in N and here the private key. And then you have this original input. So here you have here you can also put in an integer directly. And then, for example, if you try to have it convert, if you try to have it convert from integer back to string, it will display an error because sequence like this usually isn't valid UTF-8. So you can instead click keep message as integer, and it shows the original number. Here you can even put in a string. You encrypt that. Yeah, here if you decrypt it, you get something. Yeah, if the original message is a string, you can encrypt it either as an integer. You can decrypt it as an integer or as a string. Here in this window, you also have the option to select 128-bit level security. So this is so if you compare it to AES, this is equivalent to having a 128-bit long key for AES. This is 1536 bits for the primes P and Q. So 3072 bits for N and the public and private keys. This takes longer to generate. So here, now that the keys have generated, we can test these longer keys. So here we have N and E. So here we get this output. So we decrypt and we get the same that was the input.
Now I'll show you the RSA encryption and decryption using text files. I will have the value of n stored in a text file, and I have here my text file and key. Also, I will store the value of the public key E in a text file, E key, and these values will be used to encrypt my message. And I will also have an text file which will store the encrypted message. And then I have another text file that will store the decrypted message. I will select here the file for the N. Then I will select the file for the key E. And then I will use this message. So I will select the file which contains this message, which is this one. And then I will select the file which will contain the encrypted message, which is this one, text file encrypted. I will also select the option input keys for me to be able to use the text files I selected for the keys, the N and the E. And after this, I will click on the button to encrypt the message. So we can see here our encrypted message. We cannot see here the original message, which is FHSU is very beautiful. So our encryption process worked using the RSA. And then we will decrypt our message. And for this, we will store the value of D, which will be the value of the private key that will be used to decrypt the message. I will store the value in a text file. I will select the input keys option as well to use the keys that are stored in the text files. First, I will select the text file which contains the value of N. Then I'll select the text file which contains the value of D, our private key. Then I will select the file which contains the encrypted message that I want to decrypt. And then I will select the file which will contain the encrypted message. We can see that right now it's empty, so it doesn't contain any character or any message. I will select the file which will contain the decrypted message. And then after the decryption process occurs, I have here my original message here on the decrypted text file, which is the same message as the plain text. So we can see here the file which contains the plain text, and then the file which contains the decrypted message, and we have the same message. This way we finished the presentation part for the program, and as we could see, both our ASA and RSA encryption and decryption process work perfectly.
While we're implementing AES and RSA, we end up running into several challenges. First, the complexity of the two algorithms, all the mathematical concepts that we had to implement, These were a challenge of their own. Second, there is also the problem of file encodings, the inputs and text boxes, stuff in general, when encryption results in unusable characters. The last challenge we faced was using the Python takeinter library or module. Neither of us had used it before this semester, and so both of us were coding that from scratch. So building a takeinter class that we could reuse for both AES and RSA was another interesting difficulty. Overall, we need a high level of expertise and perseverance to overcome these problems.
Working on this AES and RSA cryptography project proved to be an enriching experience. Immersed in the world of encryption algorithms, we delved deeply into comprehending their inner workings. Through research and hands-on implementation, we gained comprehensive understanding of the operational mechanisms of AES and RSA cryptography, shedding light on their respective strengths and weaknesses. This project not only bolstered our knowledge of encryption algorithms, but also their pivotal role in ensuring data security. Our major takeaway from this project is the critical role of AES and RSA cryptography in safeguarding sensitive information, emphasizing the continual advancements of encryption algorithms to stay ahead of potential threats.